We're going to do two more examples of activating alcohols. The first one is going to be sulfonates, and the second one we're going to activate the alcohol with a base. Okay. Sulfonates are good leaving groups. But the nice thing about sulfonates is that they are stable, right? So previously, when we activated alcohols, we made things like OH2 plus. We made the OHPBr2 plus. We made the sulfonyl chloride plus, right? So we keep making these kind of really activated alcohols. All of these are very unstable. As soon as we make them, they react, which is good because we want our alcohols to react, right? When we start treating them with acids, that's the whole point. But sometimes you want to make something that you can then isolate and purify and use in a reaction without having to, right? You can add a different nucleophile if you can save your leaving group until later. So sulfonates we make by activating an alcohol. We react with this very reactive sulfonyl chloride, which is almost the same reaction as we saw before, right? Adds in there, kicks that out, right? We lose H plus and we get whatever our R group is. Now, depending on what the R group is, so if your R group is a CH3, this is a mesylate. So if this is a CH3, then this whole thing is called a mesylate. Right? If your R group is a benzene ring with a methyl group on it, then this is called a tosylate. And it's abbreviated TS or MS. So if you see things that look like this, right, what that means, OMS means mesylate, and that means that it's an oxygen connected to a sulfur that's connected to two other oxygens, which is connected to a methyl group, right? And so the big important point here is this is a good leaving group. Now, what's nice about this is that we're no longer limited to just halogens, right? Everything we've done up till now is adding in a chlorine or a bromine or something like that. Now we can take other nucleophiles, like, for instance, sodium azide, right? NaN3. So this is Na plus N3 minus. Now we have a good nucleophile. That nucleophile can come in, add to the carbon, kick out the good leaving group, and now we get an azide, right? Now, there's other reasons why you'd want an azide. That's not really the point here. But the point that I want to make is we can bring in a nucleophile, right? Nucleophile that is not a halogen. And this is pretty cool. This allows us to replace alcohols with anything, really, right? Anything that we can make a good nucleophile out of. So we could use the conjugate base, so a terminal alkyne, and replace our alcohol. We could convert the alcohol to a mesylate and then bring in the conjugate base of a terminal alkyne and do a substitution at that position, right? And so, which is great because that allows us to now really convert an alcohol into anything. So if we're thinking about how do we make this compound and we have something that we need to add in, if we can make an alcohol at that position, we can then convert it to a sulfonate and then do an SN2 or SN1 reaction, right? And this is great because I keep saying this is great. I hear it, I can't stop, right? It's great because we know a lot of ways to make alcohols. We have hydroboration, right? We have hydration. we have oxymercuration, we have dihydroxylation, we have all these ways of making alcohols, and now we can take those alcohols and really convert them into anything we want. So you can see the possibilities blooming around us, which is fantastic and exciting and maybe a little bit terrifying. Um, but what we also have to talk about is what if we activate these things with base? So this is a little bit of a switch here. This is called the Williamson ether synthesis. This is one of those reactions that gets a big fancy long name. It's an SN2 reaction. It's an SN2 reaction, and there's not really any other trick to it. I don't know why Williamson gets his name put on this. Well, okay, that's not fair to Williamson. He figured this out, so we should give him credit. But what's going to happen is instead of alcohol plus acid, which is everything we've done so far, now we're going to do alcohol plus base. So we recognize sodium hydride immediately as a strong base, right? H minus is going to come take that hydrogen and it's going to make the conjugate base of the alcohol, which is an alkoxide. And now we can use this alkoxide to do SN2 reactions, right? This is what Williamson figured out, is we can make ethers where the oxygen is connected to carbon on both sides if we make the oxygen into a nucleophile and then add it to a primary leaving group and do an SN2 reaction. So we can also activate alcohols by turning them into nucleophiles. Oops, there's only one there. Okay. So to sum up, acid plus alcohol equals leaving group. Great, if we're going to do something like an SN1 or an SN2, although we also saw an example where we did an E1 elimination. That was dehydration, right? Dehydration is an E1 elimination that uses activation of an alcohol. Notice that there's no E2 on this list because what do we need for an E2 reaction to take place? We need a strong base. And what do we can't have a strong base and an acid in the same reaction. You'll get the acid reacting with the base and then you just have nothing going on, right? So if you have an alcohol plus an acid, we can eliminate E2, but we can do any of the others. We can do SN1, we can do SN2, and we can do E1 if we want to do a dehydration. Okay, acid plus base, not what I wanted to do. That makes a base, a nucleophile, an alkoxide, right? All of these things. And if we have an alkoxide in our reaction, we're talking about, are we going to do SN2 or are we going to do E2, right? We're not, if we have that good of a nucleophile or that good of a base around, we're not going to be making carbocations. So there's not going to be any E1 or SN1 going on, right? How do we determine if we're doing SN2 or E2? We look at, are there hydrogens near the leaving group, right? So if there's hydrogens near the leaving group, you're probably doing an elimination. If there aren't, then you can do an SN2. And that's pretty much does it. I think that's everything you need to know about alcohols.